Hi students, this is A. Srinivas, lecturer in physics, Vignan Junior College, Vadanamundi. Students, we are talking about magnetism and matter. Already we completed 3 videos of magnetism and matter. Now we continue our discussion in magnetism and matter. In this session, in this video particularly, we are going to talk about basic definitions of magnetic field. So we describe magnetic field, or we know the information of existence of magnetic field in different parameters such as magnetic field induction B, intensity of magnetic field, and magnetizing intensity, relative permeability, susceptibility. We have some basic parameters or quantities by which we know the magnetic field in the region as well as magnetic field present in a material, determined by such parameters that will be defined first of all in basic definitions of magnetic field. Next, terrestrial magnetism. This is very important. Here in this image on the screen you are observing the image of the earth around which there are magnetic field. These are magnetic field lines, imaginary magnetic field lines are shown in this image. So the magnetic field shown by the earth is said to be terrestrial magnetism. So that will be discussed. This is a very interesting topic, students. So terrestrial magnetism, that is the magnetism of the earth, will be discussed in this video. And elements of earth magnetism, there are certain quantities that describes the presence of earth magnetic field. That quantities will be explained in elements of earth magnetic field and tangent law. Under the existence of two perpendicular magnetic field, if there is any magnetic needle, it comes to align at certain angle. We understand that angle by the using tangent law. So these are the contents that we are going to discuss in this session of the video. So let us move on to the first topic. So first one is, in first content we are describing some basic definitions to know about the magnetic field. In that, the first one is magnetic intensity. Students, the first one is magnetic intensity or magnetizing force. It is denoted by H. Magnetic intensity or magnetizing field denoted by H. So I would like to give the definition of it. This is the definition. Magnetic intensity at a point is the force experienced by a unit north pole of unit pole strength placed at that point due to pole strength of given magnet. Here students, so let me explain how to know about this definition. Suppose we have a magnetic pole. Students, we have a magnetic pole. Let this be the magnetic pole. Let us assume this is north magnetic pole. Students, look into it. Let this one be the north pole of any magnet. At certain distance are from this north pole of a magnet. At certain distance are from north pole of magnet. Let us assume unit north pole. Students, you must consider unit, especially only north pole. So let us assume a unit north pole at particular point. Then the magnetic force experienced by unit north pole, magnetic force experienced by unit north pole at this point is considered to be magnetic intensity or magnetizing force or magnetizing field. Magnetizing force or magnetizing field. The expression for that magnetizing field is H is equal to B by mu. As we know about B very well, we studied about magnetic field already and we derived the expression for magnetic field in so many cases in previous sessions. So when we know B value, B by mu is H value. According to definition, let this be the definition form. The force experienced by unit north pole at a point due to given north pole is considered to be magnetizing field or magnetic intensity denoted by H in expression form that must be equal to B by mu, where mu is the permeability of the medium. This experiment is observed in a particular medium, then B by mu. If this is calculated in free space, then this becomes mu naught. If it is conducted in any medium, B by mu. So mu is the permeability of medium. The ratio of magnetic field induction to the permeability of medium is also equal to the magnetizing field or magnetic intensity. It can also be defined as degree or extent to which a magnetic field can magnetize a substance. Suppose this is the region in which a magnetic field is present. If you introduce any magnetic material, let this be a magnetic material such as iron or nickel or cobalt. We know very well, iron, nickel, cobalt are very good examples of magnetic material. If such a magnetic material is placed in magnetic field, definitely this material may be magnetized by the magnetic field. Then it can also be defined as the degree or extent to which this magnetic field can magnetize the given material. This is the material, students, clearly representing. This material is magnetized by magnetic field. So degree or extent to which the material is magnetized by the magnetic field is also known to be the magnetizing field, magnetizing force or magnetic intensity H. Okay, let us move on to the units. So SI unit is ampere turns per meter. Students, remember it is almost equal to the SI unit of pole strength. SI unit of pole strength. So SI unit of pole strength is ampere turns here. Ampere turns per meter. Ampere turns per meter is SI unit of the magnetizing force H. So let us move on. In CGS unit is Oersted. So units are different in magnetism, so you must be very conscious about the units. So clearly remember the SI unit of magnetic intensity or magnetizing force, in other words magnetizing field, is H, expression is B by mu, and units is ampere per meter, and CGS, that is SI unit, CGS unit is Oersted. So let us move on to the next definition, that is magnetic field strength or magnetic field or magnetic field induction or magnetic flux density. All are same, denoted by B. Students, we have a clear idea about magnetic field induction. Already we defined magnetic field induction and we derived the expression for magnetic field induction caused by a pole as well as a bar magnet along axial and equatorial line. These parts were discussed in previous sessions of this video. Here, now this definition, magnetic field strength, also known as magnetic field, also known as magnetic field induction, also equivalent to magnetic flux density, magnetic flux density B. So it is in one way, it is also force experienced by unit north pole. Force experienced by unit north pole at any point is said to be magnetic field induction. In other words, actually this is the definition. Magnetic flux density, also equal to remaining 4 terms, is the number of magnetic field lines passing normally through a unit area of substance. Here, suppose if you have a region in which there is a uniform magnetic field. Okay, let this be a region in which there is uniform magnetic field. If you consider one element having certain area of cross section, this is the element considered, and through this element these are the number of magnetic lines of forces passing through that element, normal to the surface, this is the surface, so this is the normal direction. So normal to the surface, these are the number of magnetic lines of forces are passing. So this number of magnetic lines of forces passing through them by normal area is the magnetic flux density this magnetic flux density is also known as the magnetic field induction. So this is the meaning of the definition. Magnetic flux density is the number of magnetic lines of forces passing normally through a unit area of cross section. B has different expressions, we discussed about it, as B is equal to mu naught by 4 pi into m by r square for pole, or B is equal to mu naught by 4 pi into 2m by r cube on axial line of magnet, mu naught by 4 pi into m by r cube on equatorial line of a bar, sharp bar magnet. And here we are just giving a relation between B and H. B is equal to mu H. H is the magnetic intensity or magnetizing field, then magnetic field induction related to magnetizing field by this equation. As we know, mu is the permeability of that medium. And this is the known thing for us. SI unit of magnetic field induction is Tesla, also equivalent to Weber per meter square. Because number of magnetic field lines is said to be Weber. Number of magnetic field lines SI unit is Weber. By area is meter square. So Weber per meter square, which is equivalent to Tesla. This is SI unit, and CGS unit is Gauss. 1 Gauss is equal to 10 power minus 4 Tesla. That is the relation. Then magnetic flux. Here already we described magnetic flux per unit area is magnetic flux per unit area, normal to it is magnetic field induction. Then what is magnetic flux means? It is equal to number of magnetic field lines passing through given area, not unit area. Number of magnetic field lines passing through given area, normal to it is magnetic flux. So here suppose these are the number of magnetic field lines passing through given area. This is the element having some area of cross section, and area vector is this surface area is normal to the magnetic field. Surface is normal to the magnetic field. Then total number of magnetic field lines passing through area normal to it is known as magnetic flux. And the SI unit of magnetic flux is Weber. Weber is the SI unit. Okay. Then relation between B and H, already we write that relation, B is equal to mu H. Okay. Next, move on to the another definition to know about the magnetism. Here magnetic permeability, mu. So already while relating B and H, we use the term B is equal to mu H, which is known as magnetic permeability, of medium. Similarly, while writing Coulomb's law of magnetism, we wrote that F is equal to mu naught by 4 pi m1 m2 by r square. M1 m2 are pole strengths, then force of interaction between them. Then also we get mu naught. So while writing the expressions of magnetic force, magnetic field B, definitely we have the expression of mu. Now this is the time to know about this magnetic permeability. So it is the degree or extent to which magnetic lines of forces can pass or enter a substance. Suppose if you have a free space here, when you assume this is the free space, some number of magnetic field lines may pass through it. In spite of having this free space, if you replace free space by any magnetic material like iron or cobalt, we assume more number of magnetic field lines may pass through the medium. So these are the magnetic field lines outside the region in first case. When you replace the air medium, by any magnetic material such as iron, nickel and cobalt, definitely the magnetic lines which passes outside may enter through them as I shown here. So the outside lines may have possibility to pass through it for iron. This is free space. This happens for free space, and this is for iron or cobalt. If you put any other diamagnetic material, then some field lines may move outside. Very few lines may pass through it. So number of lines passing through. First case, some lines are there. In second case, more number of lines passes through the medium. In third case, very less number of lines passes through the medium. So from this explanation, we come to an idea such that the number of magnetic lines passing through given area, given region, also depend upon nature of the medium. As nature of medium changes, number of magnetic field lines passing through it also changes. That's what the meaning of that explanation. So, it is the magnetic permeability of such medium is the degree or extent to which magnetic lines of forces can pass enter a substance. So, definitely this one has more magnetic permeability, this one has moderate, and this one has least magnetic permeability. The second example, when we use a substance like iron or nickel or cobalt, more number of magnetic lines are passes through medium. So it shows that the mu is more, that is the meaning. So I hope you followed the definition with the help of this example. So magnetic permeability is the degree or extent to which magnetic lines or forces can pass through a substance. Okay, its SI unit is meter per ampere or Weber per ampere meter. So this is the first one, Tesla per meter per ampere, because the expression for B is equal to mu naught by 4 pi into m by r square, m pole strength by r square. This is the expression. The unit of B is Tesla into mu naught. This is m by r square, ampere meter by meter square means ampere per meter. On cross multiplying, we get Tesla meter per ampere. Tesla meter per ampere. Remember. So no need to by heart them units. When you have an idea about B as Tesla and the pole strength as ampere meter, we find out as I explained here. We know that Tesla is Weber per meter square. Tesla is Weber per meter square. When we replace Tesla by Weber per meter square, we have other form. Weber per ampere meter is also other unit of magnetic permeability. So next, relative magnetic permeability. Relative means we compare the magnetic permeability of a given medium. This is the medium made up of iron and this is the free space. These two have different values. Then when you take the ratio of permeability of medium with permeability of free space, that becomes the relative. Relative means by taking a ratio, we compare the permeability of medium with the permeability of free space. That is said to be relative permeability. Therefore, relative magnetic permeability is the ratio of magnetic flux density in a material to that in vacuum, or in other words, it also defined as the ratio of absolute permeability of the material to that in vacuum. Suppose when you use the material, we have absolute permeability mu, and when you consider the vacuum or free space, permeability of free space is mu naught. Ratio of those two, that is see the equation mu by mu naught. Ratio of permeability, absolute permeability of a medium such as nickel or cobalt or iron or whatever it may be, ratio of absolute permeability of a medium to the permeability of free space, that is mu naught, is known as relative permeability. Indirectly that is also equal to, because B is proportional to, according to known thing, we know that B is proportional to mu, because B is equal to mu naught by 4 pi into m by r square. If you unalter the remaining physical quantities, B directly proportional to mu, as mu r is mu by mu naught, as B is proportional to mu, mu r also equal to ratio of magnetic field in any medium to the magnetic field in free space. Hence, this is the second way of definition. It is the ratio of magnetic flux density in a material to that on vacuum. So, ratio of magnetic flux density, also known as magnetic field induction, ratio of magnetic flux density in any medium to that of free space is relative permeability, or ratio of absolute permeability of a medium to the permeability of free space is also known as the relative permeability. As it is the ratio of identical physical quantities, there are no units and dimensions for relative permeability. So let us move on to the another definition. So far we defined H, magnetizing field or magnetic intensity, remember, or magnetic field induction or magnetic flux density, magnetic flux followed by the permeability of medium and relative permeability, and units are for each one. We discussed these parts so far. Next, come on to the next definition, intensity of magnetization. Don't get confused. In today's explanation, the very first definition is magnetic intensity. Magnetic intensity or magnetizing force or magnetizing field. Because I repeatedly giving the names of the physical quantities because of only one reason, there is a possibility of getting confusion because all names are related to magnets. So don't get confused. To avoid it, so I am explaining the terms repeatedly, students. You may also try to remember and practice them. Already we defined magnetic intensity, magnetizing force or magnetizing field, that is denoted by H. Now comes to intensity of magnetization. So both are not identical. Magnetic intensity is different from intensity of magnetization. So especially magnetic intensity depends upon the external applied value. Intensity of magnetization is internally affected value by the magnetic material. So that is the difference. So intensity of magnetization, that is I, it is the degree to which a substance is magnetized when placed in a magnetic field. Suppose when you insert an iron rod in a region, an iron rod, iron is a magnetic material. When you insert a magnetic material such as iron in a magnetic field, it may get magnetized. So when you insert this iron rod in magnetic field for long time, this iron rod becomes a magnet. So iron rod get magnetized by orienting the dipoles of the substance along the same direction, it get magnetized. So that degree or extent to which a substance get magnetized when placed in a magnetic field is known as intensity of magnetization. Once again, I would like to give a major difference of magnetic intensity and intensity of magnetization. So magnetic intensity is the cause, intensity of magnetization is the effect. Magnetic intensity, we apply that magnetic intensity in a region, that is the applied one. So then the material affects for it and it induces magnetism in it. So effect was described by intensity of magnetization. Applied one are the cause explained by magnetic intensity. So that is also another difference. So intensity of magnetization is the degree or extent to which substance get magnetized when placed in a magnetic field is considered to be I. To find out the I value, that is the process in which a material is magnetized, and that phenomena is known as the intensity of magnetization. But numerically, this is the second definition. Numerically, we find out the intensity of magnetization by using the second definition. It can also be defined as the magnetic dipole movement acquired per unit volume. Suppose we have an iron rod which is known as magnetic material. Actually there is no magnetic property in it. When you insert this iron in external magnetic field, applied magnetic field, this iron rod get magnetized now. When iron rod get magnetized, definitely here M is equal to 0, there is no magnetic moment. Once it get magnetized, there is magnetic moment. So when iron material, like magnetic material, placed in uniform magnetic field, the magnetic material get magnetized, then the magnetic moment per unit volume, there is some volume for the given substance. The iron rod definitely has some volume which is equal to area of cross section into length. This magnetic moment obtained by the magnetic material per unit volume is magnetic intensity. So this degree to which the substance get magnetized is determined by the second definition. It can also be defined as the magnetic dipole moment acquired, this one acquires the magnetic moment now per unit volume of the substance. So here this is the formula. It can also be, therefore I would like to write the expression for magnetic intensity of magnetization. Intensity of magnetization is the magnetic moment acquired by magnetic material per unit volume. This is the way. So of course this magnetic moment is the pole strength into length of magnet by volume. That is area into length. Volume is area into length. So when you replace this volume by area into length, length get cancelled. So pole strength by area. In that way we get second definition. From this derivation we get second definition. It can also be defined as pole strength per unit cross-sectional area. Once this magnetic material acquire magnetism in the presence of external magnetic field, then it possesses magnetic moment. This magnetic moment per unit volume is known as the intensity of magnetization. In other words, when you extend this formula as magnetic moment is pole strength into length of magnet and replace volume by area into length, length get cancelled, so pole strength by area is also known as the intensity of magnetization. So it can also be defined as the pole strength per unit cross-sectional area. So pole strength per unit cross-sectional area, pole strength units is ampere meter by meter square, so ampere per meter. So I is equal to m by v. So magnetic moment is pole strength into length of magnet by area into length, length get cancelled. So pole strength per unit area, this is the second definition. And here the pole strength units are ampere meter, by area units is meter square, so meter get cancelled, the ultimate unit is ampere per meter. So SI unit of intensity of magnetization is ampere per meter. Already the very first definition of our discussion is the magnetic intensity denoted by H. The present part is intensity of magnetization. We are exchanging the words in that definition, in the title, then total meaning changes. Both are different. So one is the cause, second one is effect. Already explained it. So magnetic intensity is the cause, applied one. Intensity of magnetization is the effect acquired by magnetic material. But both are having same units, ampere per meter. Ampere per meter is the unit of both magnetic intensity and the present one intensity of magnetization. Students, I hope you understand the difference to distinguish between magnetic intensity and intensity of magnetization. These are two closely sounded words but having different meaning. You must be conscious about these two definitions. So let us move on to the one more definition in the parameters of magnetism, that is magnetic susceptibility, Xi-m. Here this is called as Xi-m, magnetic susceptibility. So it is the property of the substance which shows how easily a substance can be magnetized. So the significance of magnetic susceptibility, by knowing the value of magnetic susceptibility, we know about how easily that substance get magnetism. So the property of the substance, this value shows how easily a substance can be magnetized. When according to the explanation given for you already in this video, when you insert any magnetic material such as iron, cobalt, nickel placed in external magnetic field, it acquires magnetism. So it shows how easily that material acquires magnetism, and it is calculated. It can also be defined as the ratio of intensity of magnetization to the magnetic intensity. So that's why this is the reason we have the relation ratio of these two. This is the reason. Because of this I explained these two terms number of times. So it can also be defined as ratio of intensity of magnetization denoted by I in a substance to the magnetic intensity applied to the substance. Okay, don't get confused, clearly try to follow the definition. So when magnetic intensity is applied, H is applied in a region, we insert the material in that region, the material acquires magnetism. that value is determined by the I value. So finally, the magnetic susceptibility is the ratio of intensity of magnetization. It is the magnetism acquired by the material. So ratio of intensity of magnetization in a substance to the magnetic intensity. So this is the cause and I is the effect. H is the cause, I is the effect. So the acquired magnetism by applied magnetism. I by H ratio is known as the susceptibility. It shows how easily the substance get magnetized. That's why according to this definition, the magnetic susceptibility is the ratio of intensity of magnetization to the magnetic intensity, I by H. Because already I explained that H and I have same units, ampere per meter. Magnetic intensity is H, intensity of magnetization is I. Both physical quantities have same units. That's why ratio doesn't possess any units. So there is no units for susceptibility. Therefore, relative permeability and susceptibility doesn't have any units. Relative permeability belongs to the medium, and susceptibility belongs to the how easily the substance get magnetized. We know about the acquiring of magnetism by using susceptibility. So relative permeability and susceptibility doesn't have any units. Next one, relation between magnetic permeability, two unitless quantities, mu r. We know that mu r is mu by mu naught, and xi is I by h. Now the relation between magnetic permeability of a medium to the magnetic susceptibility of a substance is given by mu r is equal to 1 plus xi. This is the relation. Okay. Now I would like to describe the derivation of the relation between the relative permeability and susceptibility. So let us move on to this. Let me to describe the derivation between the mu r and xi, relative permeability and susceptibility. So relation between magnetic permeability and susceptibility. So students, let us consider a magnetic material placed in a region. Let this be a magnetic material such as iron or cobalt or nickel placed in a region. In this region already there is magnetizing field. Magnetizing field H is present in that region. Already H is the magnetizing field present in a region. The strength of magnetizing field or magnetic intensity in a particular region is denoted by H. In that we introduced a magnetic material into it. Then this magnetic material acquires magnetism. Then the magnetic field in the given material, is magnetic field in the free space plus magnetic field acquired by the medium. Magnetic field MAZ full form, let it be magnetic field. Magnetic field acquired by the medium. Students, this is the important line to start the derivation. B naught is the magnetic field in the free space. Now we introduced a magnetic material which is in this rectangular form. A magnetic material is introduced into that medium. Then net magnetic field present in the material, is B. Resultant magnetic field present in the material is B. It is sum of magnetic field in the free space which is present in the absence of material plus in the presence of material magnetic field acquired by the material medium. So once again I repeat it. Already in the free space there is magnetic field, let it be B naught. Now we insert a magnetic material in that region, then it acquires magnetic field. Because the dipoles present inside the magnetic material may orient along same direction, and the material now acquires magnetism and produces magnetic field. Then net magnetic field present in that material is the magnetic field present in the space and sum of these two, and magnetic field acquired by the medium, that is material, I mean magnetic field acquired by the material. Sum of these two is the net magnetic field in that region. Then B is equal to B naught means mu naught into H. H is the magnetic intensity or magnetizing force present in that region. H is the magnetic force present in free space. So in the absence of the material medium, magnetic field present in that place is mu naught H. We know this relation, B naught is equal to mu naught H. H is magnetizing field. In free space, if H is the magnetic field, then magnetizing field or magnetizing force. If H is magnetizing field and magnetizing force, then magnetic field in free space is mu naught H. And magnetic field acquired by the material medium is mu naught I. This implies B is equal to, let mu naught H be common from these two terms, 1 plus I by H. And magnetic field in any medium, magnetic field in any given medium, here this is the medium, so magnetic field in that medium is mu into H, where mu is the absolute permeability of medium. If mu is the absolute permeability of magnetic material like iron or cobalt or nickel, this rectangular box is magnetic material inserted in magnetic field. If mu is the magnetic permeability of that medium, then B is equal to mu H. In the medium, the expression for B is mu H. In free space, expression for B is mu naught H. Now, this is the magnetic field in the medium, therefore it is related to H by the formula mu H, where mu is absolute permeability of that medium. So, mu H is equal to mu naught H into 1 plus I by H. Here, I would like to make two changes in this equation. First, cancel H on both sides. Then take cross multiplication, mu by mu naught is equal to 1 plus I by H. Okay. Then, to get the relation between relative permeability and susceptibility, already we defined that ratio of permeability of medium to the permeability of free space is relative permeability. Ratio of permeability of medium to the permeability of free space is relative permeability, that is mu r is equal to ratio of intensity of magnetization to the magnetic intensity. Ratio of intensity of magnetization to the magnetic intensity is susceptibility, Xi. So, mu r is equal to 1 plus Xi. This is the relation between susceptibility and relative permeability of a magnetic material. Xi and mu r are the susceptibility and relative permeability of magnetic material. These are determined by the formula related by the equation Vr is equal to 1 plus Xi. Students, just I recollect the derivation once again in a moment. Here, already there is a magnetizing field H or magnetic intensity H in given region. We applied it. Now, we insert a magnetic material such as iron or cobalt or nickel in that region, then it acquires magnetic field. Therefore, total or net magnetic field present inside this magnetic material is magnetic field in free space, plus magnetic field acquired by the magnetic material. This is the due to orientation of the magnetic dipoles of the material along the applied magnetic field. This magnetic material acquires magnetic field. So magnetic field in free space plus magnetic field acquired by the magnetic material is the net magnetic field passing through it. We know that the magnetic field in free space is mu naught H, where mu naught is the permeability in free space. Magnetic field acquired by the magnetic material is mu naught I, where I is the intensity of magnetization. Then let mu naught H be common from these two terms on right hand side, 1 plus I by H. And magnetic field in the given medium is mu H, where mu is the absolute permeability of that medium. H cancels on both sides. Then take cross multiplication. Mu by mu naught is equal to 1 plus I by H. We know that ratio of permeability, absolute permeability of any medium to the permeability of free space is relative permeability, and ratio of intensity of magnetization to the magnetic intensity is susceptibility. Then mu r is equal to 1 plus xi. And susceptibility and relative permeability are the two important parameters to know about the magnetic property of magnetic material. To know about magnetic property of magnetic material, we use the values of these two and we classify them into different magnetic material. In coming videos, we discuss about classification of magnetic material with the help of these values of susceptibility and relative permeability. So let us move on to the next topic. This is a very interesting topic. So before discussing this interesting topic, we take a small break and we continue it. So students, now let me to describe a very interesting topic, that is terrestrial magnetism, terrestrial magnetic field. Earth is a huge natural magnet. Earth possesses magnetic field. Earth behaves like a very long naturally existing huge magnet. So magnetic field possessed by the Earth is said to be terrestrial magnetism. So in this next part of our video, we would like to know about what is terrestrial magnetism, what is the origin of terrestrial magnetism, that is what is the origin of magnetism of Earth, followed by what are the parameters that describes the magnetic field of Earth, also known as elements of Earth magnetism. So here in this image, you are observing the shape of the Earth. This is the Earth. And here we know that this is the equator of Earth. Students, let us observe. We know very well this is the polar axis of the Earth. This is the equator of the Earth. And this is the polar axis. Axis passing through north and south poles of Earth is polar axis. So very close to polar axis, there is magnetic axis. So in coming part, I describe it very well. So we would like to talk about all those things here, but let me to introduce what are the different points exist in knowing about the terrestrial magnetism. Here this is magnetic axis, and Earth behaves like a huge natural magnet, and it similar to this along this axis of the magnet, along this magnetic axis, let it be in form of a bar magnet having north and south poles. Here actually this the magnetic axis may not coincide with the geographical polar axis, geographic polar axis. Let the north and south poles may be like this, and here this is the magnetic field established by the Earth around the Earth in the space. Around the space of the Earth there is magnetic field established. So let me, this description is to just what are the different points to know about terrestrial magnetism. So I would like to show a video to know the origin of terrestrial magnetism. Let me to describe the origin of terrestrial magnetism with the help of a video. Here apart from textbook, students, I gather the information from the Google. With the help of that information, I am presenting the different qualities or origin of Earth's magnetism. So Let me to know about the origin of earth magnetism with the help of this video, students. Here, see, this is the earth. Let this be the north pole and this is the south pole of the earth. Students, look into this video. So I play the video with the description. Here, let this be the north pole and this is the south pole. Geographic north and geographic south poles are existing at the top and bottom, and this is the polar axis, and there is a magnetic field. Earth behaves like a huge magnet and it is along the axis, polar axis, very close to polar axis. We assume the magnetic bar magnet. We can equate the earth as the bar magnet along the polar axis, and there is a magnetic field around the earth, not only inside it, because of this bar magnetic nature of the earth, there is a magnetic field. Rose color lines in this image shows the magnetic field present. This magnetic field is present up to several thousands of kilometers. Magnetic field of the earth distributed or present to several kilometers. Magnetic field or magnetic force, magnetic field is a region up to which there is a force of attraction on any unit north pole. So if you put any unit north pole around the earth up to several thousands of kilometers, 60,000 or 50,000, they are influenced by the earth magnetic field. So hence these are the magnetic field lines present around the earth. There is some one advantage, not only the deflecting the magnetic needle, the magnetic field of the earth is not only deflecting magnetic needles on the surface of earth, it also stops some unwanted rays coming from the sun. There are so many rays reaches the earth atmosphere. Unwanted rays are prevented by the earth's magnetic field. It acts like a shield and prevents the unwanted rays, and it protects our atmosphere. Otherwise our atmosphere get polluted, get damaged by the other number of several types of the rays are coming from the sun. Not only light, actually we need visible light from the sun. Along with the visible light, so many rays reaches the atmosphere, but all those are prevented by the interaction of this magnetic field of the earth with those rays. So we are protected by the magnetic field. Students, remember, you may not know this point. So you may know in our lower classes that earth has magnetic field. That is okay, but there is a huge advantage, very important advantage of the earth magnetic field to us. That is, because of the presence of earth magnetic field and the influence of earth magnetic field to several thousands of kilometers above the earth, it prevents the unwanted rays to reach the earth atmosphere, and it is protecting us, and it avoids the polluting the atmosphere by the sun. So this is one important point that you understood. So next, let me to describe what is the main origin of the earth atmosphere. So students, one information already explained. This is not the information from textbook. From Google I get all this information. There are so many research articles written on this origin of earth magnetism. Actually, earth magnetism started 3.5 billion years ago. 3.5 billion years ago, earth magnetism was started. It is due to conventional motion of nickel and iron. Iron, nickel are magnetic material which have free electrons in outermost electron. Due to conventional motion of molten iron, nickel around the axis of the earth, the magnetic property is given for the earth. This was happened 3.5 billion years ago. So this is the geographic axis of the earth, and the earth is used to rotate. Generally earth rotates about that one. Earth behaves like a huge magnet. Students, here see the video in which you are observing a geographic axis, and earth is rotating around the geographic axis. This is the magnetic axis, very close to geographic axis. Beside of it we have the magnetic axis. Now I drawn the magnetic axis now, south to north. This is a dotted line shows the magnetic axis of the earth, which is at some angle of geographic axis, as earth is rotating about the magnetic axis here, and this is the north end, this is south end. So let us move on to the next part. So here magnetic meridian is the line passing through them. Students, wait a while, I show the origin of earth magnetism. So in terrestrial magnetism, students, you understood the terrestrial magnetism now. Okay, let me to describe it. So what I explained, you observe that same explanation in this video. So this is the earth, and student, I stop the video here. Here this is the core of the earth. This brown color is the outer core, and this yellow and orange color is the inner core. In 3.5 billion years back, there is a molten nickel and iron. Conventionally, they are rotating along with rotation of earth. Due to the motion of that one, electrons also moving conventionally. Because of this revolution of electron, it acts like a dipole and produces earth magnetism. This is the main reason of earth. So in course of the time, it gets solidified, the core gets solidified. 1 billion years back, this is the solidified core, and it produces heat from it. The heat coming from the central point, that is core, make the nickel and iron in molten state in the outside core, and as it is rotating, it continuously establishing magnetic field to the earth. So this is the explanation of earth magnetism. So once again I repeat it. Here 3.5 billion years back, everything is in form of molten state. That molten iron and cobalt, nickel, produces a conventional current around the axis of rotation and gives Earth's magnetic field. But later it solidifies and it starts evolution of heat. So heat is generated from the solidified core. Then that heat melts the nickel and iron in the outer core. Now from 1 billion years ago, from a time period of 1 billion years ago, this outer core is in molten state because of the heat generated from inner core. This outer core in molten state is still conventionally producing the currents, and that is rotation of electrons, and that produces magnetic field to the earth. So this is the origin of earth magnetic field. So let us move on to know about the elements of earth magnetism. So to know about elements of earth magnetism, here let us see this video, students. In this video I explained elements of earth magnetism, and this is the polar axis of the earth, and this is the magnetic axis of the earth. Magnetic axis is slightly making some angle with the polar axis. It is around 15 degrees or 17 degrees. So time to time it is also changing, and this is the angle between the geographic axis and polar axis of the earth. Here then we discuss about the some magnetic definitions belongs to them. One is magnetic meridian. Magnetic meridian at a place is the plane containing given place and the magnetic north and south poles. So when you comes to this part, students, here this is the magnetic axis and this is the polar axis of the earth. They are making some angle with each other. The plane that passes through the geographic axis is, we have two planes now. Let us see this video. Here the plane passing through the geographic axis is geographic meridian. The vertical plane that passes through the magnetic axis is magnetic meridian. We have two meridians. The plane passes through magnetic axis is magnetic meridian. The plane passes through polar axis is the magnetic meridian. Now let us consider some definitions from them. First one is geographic axis. Here in this image also you are observing this one. Here this is the geographic north pole and this is geographic south pole. Geographically north and south poles located at these 2 points. The axis that passing through geographic poles of the earth is geographic axis. So geographic axis is a straight line passing through the geographical poles of the earth. So it is the axis of rotation of the earth. Now because of rotation of the molten nickel and iron, conventionally there is a magnetic property of the earth. Earth is equivalent to bar magnet. That north pole of earth is located at this point and the south pole of the earth is located at this point, hence it behaves like a bar magnet. The axis passing through magnetic north pole and magnetic south pole of earth, axis passing through magnetic north pole. So this is magnetic axis. Magnetic axis is straight line passing through magnetic north and south poles of the earth. It is making 17 degrees. So time to time it is changing. It may be changes from 9 degrees to 17 degrees. In the course of time, the angle between magnetic axis and geographic axis also changing. Next, geographic meridian, the vertical plane passing through geographic axis. This is the geographic axis. You may see the image. The vertical plane passing through geographic axis is geographic meridian. And the plane perpendicular to geographic meridian is geographic equator. So horizontally, it may be probably like this. The plane perpendicular to geographic meridian is geographic equator. Next, magnetic meridian. The vertical plane passing through magnetic axis. Vertical plane passing through magnetic axis. So vertical plane passing through magnetic axis is magnetic meridian. The plane perpendicular to magnetic meridian is magnetic equator. So these are the important definitions. Next, elements of earth magnetism means the quantities or parameters which describes the magnetism of earth is elements of earth magnetism. The first one is angle of declination, theta. Let this be the geographic meridian. The brown one is the geographic meridian and bluish one is the magnetic meridian. Already in previous part of our videos and images I shown there is a vertical plane passing through magnetic axis. So let this bluish one is the vertical plane passing through magnetic axis and brown one is the vertical plane passing through geographic axis. So we have two planes passing through magnetic axis known as magnetic meridian. A plane passing through geographic axis is geographic meridian. These two planes does not coincide. They are making certain angle with each other. So angle between this magnetic meridian and geographic meridian is angle of declination. This angle here in this image you are observing the angle. So the angle between, this is the angle between the vertical planes known as magnetic meridian, geographic meridian of the earth. This angle is, so angle between magnetic meridian and geographic meridian is known as angle of declination, that is theta. That's value changes from place to place, that angle, and it varies from place to place, and lines shown on the map through the places. So this is one more definition, extension to this one. Lines shown on the map through the places that have the same declination are called isogonic. So iso means same. So the places possessing same angle of declination is isogonic lines. And line drawn through places that have zero declination is called agonic lines. So agonic lines means the lines shows having zero declination are agonic lines. So this is about angle of declination. Next one. Here, next we would like to describe another parameter. So once again consider this is magnetic meridian and this is geographic meridian, and this is angle theta, dip or inclination. Here actually the magnetic field of the earth is along this direction. This is the actual magnetic field of the earth. Suppose if you have a magnetic compass, and when you suspend the magnetic compass vertically, then magnetic needle may align in a particular direction, and this is the direction of magnetic field of earth. So take a compass box which having magnetic needle, suspend the compass vertically without any other effects. Then compass is aligned in a particular line that shows the actual magnetic field of earth. So parallel to this I drawn a vector. This is the actual magnetic field of earth. This actual magnetic field of earth is making some angle delta. So it is making some angle delta with horizontal. This is horizontal line. So here this is a horizontal line. This is horizontal line and this is vertical line. So actual magnetic field of earth makes an angle delta with horizontal of earth, horizontal position of earth. So here we have horizontal line, and this is the actual magnetic field of earth along which this magnetic needle aligns. The angle made by actual magnetic field with horizontal is delta. This is known as angle of dip or angle of inclination. Angle of dip or angle of inclination. So this delta is said to be, so the angle between horizontal component of earth magnetic field, this is BH, which is known as horizontal component of earth magnetic field. So angle between horizontal component of earth's magnetic field and earth's resultant magnetic field. This is the resultant magnetic field. This is the direction of resultant magnetic field. Because along this direction a freely vertically suspended compass needle aligns. So along this direction we have the earth's magnetic field, and this is the horizontal surface of the earth. So along this direction we have the horizontal component of earth magnetic field. Then angle between the horizontal component of earth's magnetic field and earth's resultant magnetic field at a place is known as angle of dip or angle of inclination. That is denoted by delta here. Here it is 0 at the equator. Very important point is at equator this angle of dip is 0. At poles angle of dip is 90. Because when you reaches the pole of the earth, the magnetic needle may align vertically. Then with horizontal it is making exactly 90 degrees angle. So angle of dip it changes from position to position on surface of earth. Angle of dip exactly at the equator becomes 90 degrees. At poles, angle of dip at poles is 90 degrees and 0 at equator. So lines drawn upon a map through places to have the same dip are called isoclinic. So the line drawn through places that have 0 dip means generally 0 dip is possible at poles, known as aclinic. Now horizontal component of earth magnetic field. So total intensity of earth's magnetic field does not lie in any horizontal plane, as I shown in previous video. Actually magnetic field is along a particular direction. Then the component of that magnetic field along horizontal is known as horizontal component of magnetic field. So here you follow this definition. The component of the earth's magnetic field along horizontal at an angle delta is horizontal component of earth magnetic field. The component of actual magnetic field of earth along horizontal is known as horizontal component of earth magnetic field. Here because the actual magnetic field is along this direction and this is the horizontal component BH, the angle between actual magnetic field and horizontal component is known as the delta, known as angle of dip or angle of inclination. In this right angle triangle, when you consider cos delta BH by B, cos delta BH by B, then BH is equal to B cos delta. Then similarly, this is the vertical component of earth magnetic field BV, and consider sin delta, this is also equal to BV. Consider sin delta, that is equal to BV divided by B, then BV is equal to B sin delta. BH is equal to B cos delta is the expression for horizontal component of earth magnetic field. BB is equal to B sin delta is the expression for vertical component of Earth magnetic field. Then when you squaring and adding the equations, BH square plus BB square is equal to B square, then B is equal to square root of BH square plus BB square. So next one, this is the very important explanation, student. The horizontal component of Earth magnetic field, vertical component of Earth magnetic field, and horizontal component, the component of Earth magnetic field along horizontal is BH, expression is B cos delta. Component of Earth magnetic field along vertical direction is vertical component of Earth magnetic field, that is B sin delta, where delta is the angle of dip. Then B is also equal to square root of BH square plus BB square. Next comes to tangent law. Suppose we have a magnetic needle lies along a particular magnetic field B2. Initially along this direction there is B2. Along B2 a needle lies initially. Now when we apply B1, as a resultant it comes to equilibrium at particular angle theta, then tan theta, along this direction we have B2. So tan theta is equal to B2 by B1. If magnetic needle is suspended in a region where two uniform magnetic fields are perpendicular, B1 is one magnetic field, B2 is another magnetic field. These two must be exactly perpendicular to each other. We have two perpendicularly directed magnetic field as B1 and B2. If you suspend any magnetic needle, pivot any magnetic needle in this region, then magnetic needle may comes to equilibrium by making theta angle with a particular magnetic field V1. Then tan theta is equal to opposite side by adjacent side. So it comes to align or comes to equilibrium at an angle theta such that tan theta is equal to B2 by B1. Hence this is the Earth magnetic field and tangent law. Students, in today we discussed about basic definitions of magnetism such as magnetic intensity, magnetic field, and intensity of magnetization, relative permeability, susceptibility. And we described about the terrestrial magnetism, origin of terrestrial magnetism, and followed by elements or quantities to describe about horizontal component of Earth's magnetism. Okay, students, so I hope you followed this lesson very well with this video and images explanation about magnetism. Thank you for watching. Thank you, Vananda.